Aloha BIOCHEM. In this video we continue in Chapter 9 and discuss acid-base reactions. So this time we cover sections 9.2 and 9.3 on acid-base reactions and acid and base strength. Let's first recall in our previous lecture we introduced acids and bases. Acids are compounds that release protons when they dissolve in water, and they donate protons when they chemically react. And that means when they react with bases. A couple of examples are hydrochloric acid, which is a strong acid, and hydrofluoric acid, which is a weak acid. Strong acids completely ionize in solution, so every single molecule of HCl ionizes into protons and chloride minuses. Weak acids, on the other hand, only partially ionize, so although you get some protons and some fluorides, the majority simply dissolve as whole molecules. Bases, on the other hand, release hydroxides and water, and when they react with acids, they accept those protons that the acids are donating. A couple of examples are sodium hydroxide, which is a strong base, and ammonia, which is a weak base. Like strong acids, strong bases also completely ionize, so every single NaOH ionizes into Na pluses and OH minuses. Weak bases, on the other hand, only partially ionize, and so you get some hydroxides in water. And the way you get hydroxides from weak bases, by the way, is the weak base molecule takes a proton from water. It takes one of the protons, and that turns it into NH4 plus, and then the water, after losing the proton, becomes OH minus. So only some of the molecules do that, but the majority of the weak base simply dissolves as NH3. Now acids do like to react with bases, and in this lecture we discuss such reactions, and we'll compare what happens when strong acids react with strong bases, and also weak acids react with weak bases, and we'll even mix and match and see what happens when strong acids react with weak bases, and so on and so forth. So, acid-base reactions are called neutralization reactions, and these are known as proton transfer reactions. Remember, acids like to donate protons, and bases accept those protons. So the protons are transferred from acids to bases. In our first example, we see what happens when a strong acid reacts with a strong base. For our acid, we select hydrochloric acid, and our base, sodium hydroxide. We'll just write the hydroxide in the chemical equation up here, but the sodium is still there. The reactants can be visualized in the beaker here. This is a strong acid, so it's completely ionized in solution, and strong bases are as well. So acid-base reactions are proton transfer reactions. The acid donates the proton over to the base. So here's the base accepting that proton. And after it accepts the proton, it turns into a water molecule. And here are the products. You have your water, and then after the acid loses the proton, it's chloride. And so when strong acids react with strong bases, you simply get salt water. Now, once the acid loses its proton to become the chloride, we call this the conjugate base of that acid. It's what's left after it loses the proton. And likewise, once the base gains the proton to become water, we call this the conjugate acid of that base. So these two form what's called a conjugate pair, and those two also form a conjugate pair. And there are always two conjugate pairs in an acid-base reaction. So the HCl and the Cl minus are one pair, and the OH minus and the H2O are another pair. The difference between the acid and the base form of a pair is always just a proton. So if you take a proton away from this, you're left with that. And if you give a proton to this, you're left with that. On the product side, you call them conjugates. So this is the base and that's its conjugate acid. And then this is the acid and that's its conjugate base. But I like to think of them as simply a conjugate pair. So these two are a pair. This is the acid and that's the base form. And these two are another pair. That's the base and that's the acid form. In our next example, we look at a strong acid reacting with a weak base. And this time for our weak base, we select ammonia, NH3. This is a strong acid again, so it's completely ionized in solution. But weak bases, on the other hand, most of it is simply dissolved as molecules. So I've just drawn the molecules here, and one of them I've represented as its Lewis structure. Acids donate protons to bases, and so here's the base accepting that proton from the acid. And after it accepts the proton, these lone pair electrons form the bond with the proton to form the NH4 plus. And what you're left with is, the chloride, and you still have some ammonia left over. Now again, you have two conjugate pairs in an acid-base reaction. After the ammonia accepts the proton to form NH4 plus, this is the conjugate acid of that base. If you give a proton to this, it becomes that. So this is the acid form and that's the base form. Then HCl and Cl minus are another conjugate pair. If you take a proton away from the acid, you're left with its conjugate base. So two conjugate pairs. Now, unlike the previous reaction, this one does not go to completion. Okay, so not all of the reactants form products, and that's because we're dealing with a weak base this time. The difference between a strong base reacting and a weak base reacting is the weak base, kind of wants to accept protons, whereas the strong base really wants to accept protons. So in the first example, you have a strong acid which really wants to donate protons, reacting with a strong base which really wants to accept those protons. And so that's what they do, and they form the products. In example 2, you have a strong acid, again, which really wants to donate protons, but it's reacting with a weak base which kind of wants to accept those protons. And kind of wants to means there might be a few base molecules that are left over, not reacting, okay, at the end. And so that's what this backwards arrow represents. Now, most of the reactants form products, but there is probably still a few reactants left over. Okay, so this is an equilibrium arrow, and since the forward direction is longer than the reverse direction, I would say that the products are favored here. So most of the reaction proceeds to products, but there is still a little bit of reactant left over at the end. This reaction has a medical application, by the way. When hydrochloric acid reacts with ammonia, ammonium chloride is formed, and this is a mucoactive agent. So it's used in some medicines to help thin out the mucus in your trachea and especially your bronchial region, so you can clear your system out and breathe better. In our third example, we see what happens when a weak acid reacts with a weak base. So maybe you can predict what happens this time. You have even less reaction proceeding because both of them are weak this time. For our weak acid, we select hydrofluoric acid, and we'll stick with ammonia for the weak base again. These are both weak, and so they dissolve primarily as molecules. They do not ionize, most of them do not ionize, and so they're better represented as molecules in solution, and most of the NH3 is dissolved as molecules. Now, acids donate protons to bases, which accept those protons. So here's one of the ammonia molecules accepting that proton from the HF. It literally has to take it from the molecule. So these electrons form a bond with that H, and then those two electrons go back to the fluoride. And so after accepting the proton, it turns into NH4 plus, and then you're left over with F minus. And so you can see the products over here are NH4 plus and F minus. And you can probably spot the two conjugate pairs. So you have HF and F minus form one pair. This one has the proton and this one doesn't have it. So this is the acid form and that's its conjugate base. And these two form the other pair. This has the proton and that doesn't. So this is the acid form and that's the base form. So on the product side, we label them as conjugates. So the conjugate acid and the conjugate base. So again, you have two pairs in every acid-base reaction. Now, these are both weak this time, and even less reaction occurs. So I've drawn a longer backwards arrow for the equilibrium arrow this time. But I would still say that the products are favored. The forward arrow is probably still a little bit longer than the backwards arrow because although this is a weak acid and this is a weak base, they're not really weak, okay? So this weak acid kind of wants to donate its proton, and this weak base kind of wants to accept it. And I would say, you form more products than you have reactants left over at the end. So I would still say products are favored, but you do have quite a bit of reactant still left over anyway. Now, there is a whole spectrum of weakness for both acids and bases, and we can see perhaps more clearly in this table right here. So here is a list of acids in order of decreasing strength. So at the very top, we have the strongest acids. This is not a complete list, by the way. So just a few acids here. But at the very top, you have strong acids. So you have hydrochloric acid, nitric acid, anything that gives you protons in solution, fully ionized protons in solution is a strong acid. So these are kind of equal strength, 100% ionization. Okay. Now, as you go down this list, outside of this highlighted region, you get into the weak acid region. So only some of these molecules ionize, and as you go further down this list, less and less of them become ionized. Where, if you go way down here, HPO4 minus 2, maybe, 1 out of every trillion molecules ionizes. Whereas up here, near the top of the weak acid region, maybe 1 out of every 5, or 1 out of every 3, or 1 out of every 15. So, you get much more protons in solution versus down there. Now, weak acids. So again, as you go down this list, the acid, gives you less protons in solution, but it also doesn't really want to donate its proton when it's doing a reaction. Okay, it's less likely, it's less likely to donate its proton over to the base. Okay, it's not very pushy, in other words, as you go further down the list. The strength of these weak acids can be quantified by what's called the Ka value. This is the dissociation constant, which we'll talk about more in the next lecture. But basically, the smaller the dissociation constant, the weaker the acid. And eventually you get down to, water, which has a dissociation constant of 10 to the minus 14. So water even can act as an acid, but it's just so weak. Okay, so as you get down this list, you get to weak acids that are almost as weak as water itself. Now, on the right side of this table are a bunch of bases. And in fact, these bases are the conjugate bases of those acids over there. Okay, so look, take any one of these. If you take a proton away, you're left with its conjugate base. If you take a proton away, you're left with its conjugate base. So if you take a proton away, you're left with its conjugate base. So these are all the conjugate bases of those acids. Now, as the acids get weaker and weaker and weaker, their conjugate bases get stronger and stronger and stronger. And eventually, you get down to the strong bases down here. Okay? The strong bases down here. I hope that makes sense that as the acids get weaker, the conjugate bases get stronger, or as the acids get stronger, the conjugate bases get weaker. Because think about this. When you get to stronger and stronger acids, these guys up here, really want to donate protons. And after they donate a proton, this is what's left, and these don't want the protons back. Why would the conjugate base want that proton back when these really want to donate it? Okay, so think of it like that. When you have strong acids, or even the stronger of the weak acids, producing lots of protons, their conjugate bases don't really want them back. So these are very weak bases. They don't like to take any protons, and they don't want them back from their conjugate acids. Okay, but when you get to weaker and weaker acids, they don't really like to give up their protons, and their conjugate bases, on the other hand, want protons. Okay, think about it. These acids down here are comfortable as is. They don't want to give up their protons. In fact, they would like to stay as is. And their conjugate bases, will simply grab protons to form those guys, because this is how they want to be. Okay? So these guys want, so when you get down to the bottom of the base portion of the table, these stronger and stronger bases are trying to turn into those guys. Okay, they're trying to grab protons to turn into those guys. And as you get to the top of the acid table, these guys are trying to donate protons to turn into those guys. So when you do an acid-base reaction, in order to have the reaction proceed to products, you want to combine a substance which really wants to give up a proton with a substance that really wants to take it. So select someone up here with someone down there. If you try to select someone over here with someone over there, it's not going to go to completion, okay? Because here you have a weak acid. It doesn't want to give up its proton, and you're trying to react it with someone who doesn't want to accept it. The reaction's not going to go. So don't do this. Do that right there. And so for example 4, let's react a stronger weak acid with a stronger weak base, and we'll select acetic acid and methylamine right there. So here, these two, that's the direction. This slanted way. I'm trying to do it the same way as on the. Okay, there you go. That way. So so here's the weak acid. There's the weak base, and acids donate protons to bases, and so after it does, the acid turns into that. This is the conjugate base of that acid, and after this accepts the proton, it turns into that. This is the conjugate acid of that base. Again, you got 2 conjugate pairs in an acid-base reaction, and since you're reacting a stronger weak acid with a stronger weak base, the products are favored. So the forward arrow is longer. In example 5, our last example, we'll select HCN and we'll react that. That's hydrocyanic acid. We'll react that with the bicarbonate anion. So here you're going in this direction. That's not going to go towards product as much. And you'll have some of the reaction occur, and so this acid donates some proton to that base, and after it does so, it turns into cyanide ion, which is the conjugate base of that acid. And after this accepts some of those protons, it turns into carbonic acid. This is the conjugate acid of that base. So you got two conjugate pairs again in the acid-base reaction, but this time the reactants are favored because it's a really weak acid reacting with a really weak base. So I hope you get that. The author has a table in the textbook. This is table 9.3, acid dissociation constants. So here's a bunch of acids and their acid dissociation constants, but there's one more table I wanted to show you here. Table 9.2. So table 9.2 shows you a similar looking table as I've drawn over here. It doesn't include the acid dissociation constants, but again, it shows the acids. You got your strong acids up here. So you got your strong acids up here, and you get weaker and weaker and weaker. And then their corresponding conjugate bases get stronger and stronger and stronger. So if you want a reaction which proceeds mostly to product, okay, select someone up here with someone down there. Okay, if you try to go this way, the reactants are going to be favored. So that's how you can predict whether the products are favored or the reactants are favored in an acid-base reaction. In our next lecture, we will discuss more on acid and base strength, and more specifically the acid dissociation constants. And pretty soon we will be doing the pH. So get ready for that. Aloha.